both switchboard manufacturers and specifiers, modern building designs, shorter lead times, the demand for integrated solutions and higher fault levels are making the selection of appropriate forms of circuit protection increasingly complex. And although a wide range of performance considerations complicate the choice even more, there are in the end only two basic options for providing circuit protection for LV switchboards. Both moulded case circuit breakers, or MCCBs, and HRC fuses have advantages and disadvantages. But until now, the choice of either option has been based on technical information provided by their manufacturers and marketers. Now, a comprehensive series of comparative electrical tests has been conducted to verify the performance data supplied by the various fuse and MCCB manufacturers. All the equipment tested was new, and the tests were conducted in accordance with international standards. As well as verifying specifications, a range of more general claims and counterclaims were also tested in the process, with a focus on crucial considerations such as operational consistency, protection of associated equipment, operating speed, let-through levels and operator safety. To begin the tests, various brands of MCCBs were selected, with a rated interrupting capacity equal to or greater than 63 kA. Because MCCBs are designed for simple resetting after each fault interruption, resistance measurements were recorded before and after every test to measure any contact deterioration. All the tests were filmed, so the results could be visually displayed and verified. After one operation, the contact resistance of this 400 amp circuit breaker increased 4 times. Clearly, it will be unsafe to reset this breaker and expect it to operate within specification. An inspection of the contacts also revealed significant damage. This second breaker was extensively damaged. Arc products exhausted out of the device, causing additional arcing on the line side bus bars. Respected electrical engineer Peter Crosley comments.
After the first test, certainly the integrity had gone. As you say, the contact resistance clearly went up each time. My main, biggest sort of concern out of this test is that there's no clear visible sign that the breaker was damaged. The integrity of the breaker certainly has deteriorated. The second breaker was clearly unserviceable. We couldn't use it again. It virtually vaporised internally. Parts of the breaker went right across the test station. And that certainly would have, probably would have killed the operator.
The third 400 amp circuit breaker created a massive arcing fault, and clearly anyone in front of this MCCB would have been severely injured or killed. The breaker blew off the panel and started fires in the test cell. The view from the second recording camera shows the extent of the blast. In slow motion, molten metal can be seen escaping in all directions. The next step in the tests was to compare the performance of 400 amp HRC fuses when subjected to the same test. In this case, the result of interrupting the fault was completely contained inside the fuse body. Internal inspection revealed that the elements had fused into fulgurite. As designed, the fuse had been sacrificed, but it had done its job in isolating and fully containing the fault, saving any nearby operators from harm and protecting surrounding and downstream equipment. Following this initial set of tests, a second set of make and break tests was conducted to ensure the performance of MCCBs and HRC fuses had been fully assessed under fault interruption conditions. Again, these were comparative tests, conducted with new circuit breaker and fuse equipment in accordance with international standards. After one operation at 63 kA, contact resistance had increased significantly, and the MCCB had a crack in its case. There's no particular reason maintenance staff resetting this breaker would have noticed this crack, and in any case, they would have had no way of knowing that its resistance had increased to a degree that made it incapable of operating effectively. With its resistance increased well beyond specification, subjecting it to a second break shot at the same amperage showed more visibly dramatic results, with significantly more material emitted. With 2 short-circuit trip tests completed, a closing test was attempted. This test simulates an operator closing the breaker onto a short circuit. It could be argued that this rarely occurs, but as we've seen, the ease of resetting a breaker means that no specialised knowledge or understanding of the possible consequences is required to perform the task. The next step was to perform a test on a 630 amp fuse with the same prospective current as the MCCB break tests. The 630 amp fuse cleared the fault faster than the MCCB and did so without any emissions whatsoever. The 250 amp MCCB is one of the most common sizes used. Often used in multiples on a chassis, this MCCB performed its first trip with substantial emissions and an increase in contact resistance of more than 40%. The same trip test, performed on a 250 amp fuse, produced no emissions at all. Its energy let through too was over 30% less than that of the 250 amp MCCB. The next test was a make shot on a 250 amp fuse. Here we do see some minor flashing from the contacts of the switch fuse, and this is not unusual as the contacts actually make onto the short. But this presents no danger to an operator and no likelihood of damage to any surrounding or downstream equipment. Finally, we see the same make shot, this time with a 250 amp circuit breaker. In comparison to the minor and contained flash that emanated from the 250 amp fuse switch, we can see substantial emissions that would undoubtedly injure any nearby operator. The MCCB also took longer to clear and let through more than double the energy to the downstream circuit. Throughout this video, we have seen MCCBs and HRC fuses alternately performing identical tests. Viewers will draw their own conclusions, but there are some observations on the operation of each of these protection systems that can be made without fear of contradiction. After every test, MCCB contacts deteriorated substantially. This would lead to significant heat rise in switchboards, adversely affecting the performance of surrounding equipment.
Certainly, if we were able to put that breaker back into service, we would have a higher heat rise problem in the switchgear.
Although MCCBs are designed for quick and easy resetting, damage sustained during fault interruption means in many cases they need to be replaced. In conjunction with damage sustained by associated equipment, this can entail considerable downtime and expense.
Certainly the downtime with the circuit breaker, and in particular the second circuit breaker, would have meant that a fair bit of switchboard rebuild would have had to have occurred, which wouldn't have happened with the fuse. But I think we should mention that we were interrupting a full level fault in this case.
MCCBs can present a physical danger to operators and building owners. Specifiers and switchboard manufacturers need to consider this when selecting and approving circuit protection systems. The penalties for failing to ensure a safe working environment can be substantial, and company directors are personally liable for employee safety. Higher energy let-through with MCCBs poses significant risks to downstream equipment.
Or the cables moved around much more when we were operating on the circuit breakers, indicating that there was a much greater let-through energy than in the fuse situation. So there's much more potential for damage.
MCCBs require complex discrimination calculations. Amongst many other factors, fault levels, impedance and operating times must all be considered. Although they must be replaced after every fault, the ability of fuses to contain energy within their bodies means that no danger is presented to nearby operators or to surrounding equipment.
Certainly the fuse panel worked well, the fuse switch worked very well. And there was no sign of any damage when we actually closed it onto the fault. The first test where we just closed the supply onto the fuses already faulted, and the fuses cleared the fault. Now that was fine, but the second test where we actually closed it
onto the fault
using the mechanism didn't damage the CPS unit.
After fault interruption, fuse replacement downtime is inevitable. However, it is definable and predictable, being limited to the time taken to replace the fuses. There are no dangerous emissions or sudden showers of superheated debris associated with fuse operation. Lower energy let-through and faster operating times mean less damage to downstream equipment. Replacing fuses restores 100% circuit integrity. Discriminating with fuses is by the simple ratio of 1 to 1.6. In the comparative tests seen in this video, the MCCBs and fuses used were subjected to exactly the same fault interruption demands under exactly the same conditions. With their demonstrated ability to interrupt very high currents while fully protecting downstream equipment, and most importantly, ensuring complete operator safety, HRC fuses clearly and substantially outperformed moulded case circuit breakers.
Made me jump back. I thought it been anyone else.
That wasn't a back.